So our first speaker today is from St. Louis University. His name is Brandon Gillis. If you're looking at the session list on the whatever you call this, organizing piece of paper here, he is shown as 3, but due to some flight complications, we're moving him to first. So it's going to be the rest of the order after that. We're just moving Brandon here first. But anyway, he's going to talk to us about the evaluation of the orientation of concrete finish machines in skewed bridges using finite elements. So
good morning, everyone. So I'm Brandon Gillis. I'm a master's student at my university, and I'm one of the co-authors. Faress and Lee were the main investigators of this paper, and they couldn't be here. So since I'm the only one that have the least hassle getting back to America without any immigration or visa issues, I'm here instead. We're going to start with an introduction, then give a background on some of the information, outline our research objective, talk about how we modeled it in finite element analysis, and how we created a reference bridge to compare all our data to, and how we oriented the SCREED machine, and talk about skew angle, and then I'll tell you our conclusions. In bridge decks, there's usually a deck slab overhang. And so this is the width of the deck that extends from the center line of the exterior girder out to the edge of the deck. And usually it's there to allow for a much more expanded roadway without having to add additional exterior girders or additional girders to the bridge. So there's usually some limitations based on various state DOTs. Texas says that it has to be less than either 3.33 feet or 1.3 times the girder depth, and every state has its own limitations on how wide your overhang width can be. During the construction process of concrete deck steel girder bridges, there's a lot of loads that occur. So one of them is the fresh concrete. So as the deck slab is being poured, the concrete slowly encroaches across the entire span of the bridge, and that contributes heavily to the loads being applied to the girders. Additionally is the SCREED machine that smooths out and pours the concrete onto the deck itself too. And since it's, as you can see here, it travels along this overhang formwork here, and there's rails on here where the SCREED machine will slowly pass along the entire span of the bridge, and that causes additional loading to the exterior girder. And then there's the overhang formwork and construction personnel. However, they don't significantly contribute to the entire loading compared to the load of the concrete and the load of the SCREED machine. When you have the SCREED machine on these rails that are extended out on the formwork that are attached to the exterior girders, it causes torsion to occur, and it causes a moment, which causes these exterior girders to rotate outward from the bridge. And if it's excessive enough, it can cause a couple of issues such as a thin deck, lower concrete cover, poor rideability, and other things. There's one of two ways in a skewed bridge that the SCREED machine can pass over the bridge. One is a parallel configuration, where it's parallel to the skew, and it crosses over equally along each of these girders. And then the other option is perpendicularly, where it will give you perpendicular to these girders and cause unequal loading along the entire each girder. So a couple of things that we wanted to achieve in the study was, one, we wanted to figure out which traveling orientation produces less rotation in these exterior girders. Another was to see how rotation is affected by the SCREED machine orientation. We wanted to see how different wheel load distributions affect the rotation, and how different skew angles can affect the rotation in the exterior girders. What we did first was we had to use an FE model to do this, and so we validated by comparing to a bridge we studied in Madison County in Illinois. And so we field monitored this bridge and got actual field results from it. And then we modeled it in SAP 2000, our computer program at our university, and we were able to reconstruct it here as entire bridge. We used frame elements for the formwork, and then shell elements to create the girders and the diaphragms, and rigid links to create the simulation of the bolts and welded connection. And so we compared the results between the field results and our FE model, and we found that there was only the max difference between the rotation values was about 24%, and the difference in strain values was 23%, and we said this was acceptable because there's no way to completely perfectly model an a construction process in FE, since there's a litany of different factors that can affect the final product. We decided to look at the midspan of the bridge between the two piers of the original bridge to keep it simple as possible and to focus solely on how the skew and how the orientation affects the bridge. We first modeled it with a 0% skew, 0 degree skew, to get a test of how the rotation values were and to create a control base. And then we altered it to a 15 degree, 30 degree, and a 45 degree skew. And the diaphragms were staggered perpendicularly within the bridge. However, at the ends, they were parallel to the girders based on IDOT recommendations. And so we then tested both orientations of the SCREED machine, one with parallel to the skew and one perpendicular to the skew. And we also found that a SCREED machine can have different kinds of wheel configurations. Usually it's 4 wheels on each railing, but there can be a third wheel assist option, which will allow 6 wheels on both rails, which would redistribute the loading of the SCREED machine. So we tested that too. And in the parallel configuration, the SCREED machine actually has to be extended more as the angle increases. And so they do this by adding more truss members, making the SCREED machine longer. And when they do that, they add more weight. And we found that the weight increased minimally for 15 and 30, but significantly at the 45 degree, about 13.6%. We kept the weight the same at the 0 degree for 15 and 30, but we kept the weight here for 45 degrees to test if it was a significant contribution to it. We had the machine travel every 2 feet, then we record the rotation at the center of the webs every 2 feet for the entire length of the bridge. And what we found in our results for the 0 degree skew was the maximum outward rotation in G1, G6, and here. G1 would be this exterior girder here, and G6 being this exterior girder up here, was about 0.282 degrees for both G1 and G6. And they occur approximately near the center at the midspan of 2 diaphragms. So about approximately right here, which is accurate, pretty accurate for this kind of loading. We found then our stable rotation, these lines here, was about 0.0447 degrees, and the stable is when you remove the SCREED machine and all that's left is a concrete loading. So this is the rotation that stays within the bridge. And then we tested the third wheel assist with 6 wheels on both rails to see if there was a major difference, but it only had a 8% effect on it, so we considered this insignificant, and we just kept 4 wheels on the rails for every other skewed bridge. And so these are our results for the 15 degree skew. So these two are the parallel configurations, and this ones are the perpendicular configurations. For G1, the maximum occurred here towards the center between 2 diaphragms, and the parallel at G6 occurred towards the end span in between 2 diaphragms there. They were approximately equal rotation values on both here, but for here in the perpendicular, they occurred in the same place. However, G6 didn't have much of a rotation compared to G1 at the maximum for G1, and G1 didn't have one for a maximum of G6. So they were kind of more flatlined there. And so here is the stable rotations in the exterior girders after the removal of the SCREED machine. And as you can see here, compared to what it was here in a 0 degree skew, it's much more different. It starts at a 0.2 degrees at one end and goes to negative 0.2 on the other end. So while they do end at the same, there's this noticeable curve here. And this is due to what we call differential deflection. Here, when we do perpendicular, there's unequal loading of the concrete on the girders themselves. Whereas G1 gets a lot of concrete, G6 always gets less concrete than G1. And this causes different deflections on the girders. So where this one's at a diaphragm, this one's in between a diaphragm, so it causes different deflections, and this causes unbalanced rotations to occur, causing more torsional moments on the exterior girders, leading to this to occur. Then these are results for all the other skew angles. There is a noticeable increase as the skew angle increases. Between the parallel and perpendicular, using a perpendicular increases the rotation in G1 significantly, but for G6, it's approximately similar to each other. And then these are the stable rotation values that increase as the skew angle increases. What we found in our research was that if you move the SCREED machine perpendicular to these girders, it causes unbalanced loading of these girders due to the concrete pouring on the deck slab. And these unbalanced loads, they magnify the differential vertical deflection in these girders, and this increases rotations in the exterior girders and dramatically more so in one than the other, because one girder will always have more concrete than the other girder just because of how it's skewed. And it depends on also how the SCREED machine moves compared to this way or this way. And so we found that if you move the SCREED machine parallel to the skew, it creates a more balanced rotation in the exterior girders, and that we recommend using a parallel orientation rather than perpendiculars to avoid large unbalanced rotations to occur throughout the girders. We found also that the third wheel assist doesn't really affect the rotations too much, and that the increase in machine weight on the 45-degree doesn't increase it too well. And while there's noticeable differences between various skews, that's part of a future research that we're doing right now to see how the skew angle affects rotation in a more in-depth analysis. So, thank you. Any questions?